a lot of function types, for instance, linear functions, quadratic functions, exponential functions, and so on. And now we want to discuss some general properties of real functions. So all the function types that we know are called real functions because they take real numbers as values and they return real values again. So one of these properties will be continuity. We will discuss turning points, the asymptotic behavior, and curvature. So to start with continuity. A function is called continuous. So there is of course an exact mathematical definition, but you can imagine continuity of functions like this, that a continuous function graph can be drawn in one line, so without removing the pen from the paper. For instance, let me draw a continuous function graph. This could look like this. So I only used one line to draw this function graph. We also know discontinuous functions, so this one is continuous. And a discontinuous function could, for instance, look like this. Variation models with a negative power, they can look like this. This would be the positive part of it, and this would be the negative part of it. So to draw this, I have to draw two lines which are disconnected, and that's why this function would be called discontinuous. Actually, the formal mathematical definition is a bit different because there is a way of how you can define even a function like this as being continuous, but for the imagination it's sufficient to think about continuous functions that you can draw in one line and discontinuous functions that you cannot draw in one line. Well, next one, the turning points. We only talk about turning points if functions are continuous or in a region where they are at least continuous. So turning points mean minimum and maximum points. So if I draw another function graph, let me do it like this. So this function graph has a minimum turning point here, so we could call it min1 for minimum, first minimum turning points. There is another minimum turning point here, and there are maximum turning points here and here. These turning points are also called local minimum points or local maximum points. Yes, and a function is called increasing if whenever you come from the left and go to the right, then you have a slope that goes upwards, and it's called decreasing if it goes downwards. So functions can also mix increasing and decreasing regions. So for instance, this function would be, if you are asked to describe it, then you would say that it's decreasing in this region, that it's increasing from the first minimum to the first maximum, that it's decreasing again this region, it's increasing between this minimum and maximum, and it's decreasing again after the last maximum. So you could also state this in the following form. The function is decreasing in, and now you could state the interval where it's decreasing. So let's assume that this is, if this is -1, -2, let's say that this one equals -3.5 and -2.5 for the maximum, and 0.5 for this minimum, and 1, 2, 3.5 for this second maximum. So the function would be decreasing in the interval from -infinity to -3.5. It would be increasing in the interval from -3.5 to -2.5, decreasing again in -2.5 until +0.5, and increasing in 0.5 to 3.5, and decreasing again in 3.5 to +infinity. Let's talk about asymptotic behavior. An asymptote is a straight line that the function graph approaches. Usually it never reaches an asymptote, but it approaches it to any given degree of closeness. So for instance, if we have a exponential function, a falling exponential function, a decreasing exponential function, this could look like this, and the function graph is approaching the x-axis, but it will never reach the x-axis. So in this case, you could say that the x-axis, so this line, by the way, the equation of this line, the equation of the x-axis would be y equals 0, because you specify the x-axis by telling that there is no y coordinate. So y equals 0 is a horizontal asymptote of this function graph. Some functions also have vertical asymptotes. Let's draw one. Let's draw the this power function with power -1 again. So the inverse variation looks like this. It has actually two asymptotes. It has a horizontal asymptote. The x-axis is a horizontal asymptote. And the y-axis would be a vertical asymptote. An equation for the y-axis, by the way, would be x equals 0, because you specify the y-axis by telling that there is no x coordinate. Okay, one more. The so-called curvature. In German we call it Krümmung, so it tells you in which direction a function graph is curved, or in which direction a function graph bends. Let's try to draw a nice function. For instance, this function graph has several regions of curvature. So if you would start like this, and you imagine that it's a street and you are driving along it in a car or on a bike. So the first thing that you would have to do is that you have to turn to the right. So this is a curve to the right, and curves to the right, they are called negative curvatures. So they are also, so it's to the right. We call them negative curvatures. There is a positive curvature here because you would have to turn to the left. By the way, there is a very nice analogy how you can memorize these positive and negative curvatures. A positive curvature looks like this, and a negative curvature looks like that. So we have a negative curvature here and a positive curvature here. We could just draw these. So negative curvature here, positive curvature here, and obviously there has to be some point in between the region of negative and positive curvature where the one curvature ends and the other one begins. I'm now just estimating the position of this point. It could be somewhere here. So the point which is between the positive and the negative curvature, and points of this type, they are called inflection points. So this would be an inflection point. Let me draw another graph. It has a lot of turning points and curvature information. So in this case we would have positive curvature, then negative curvature again, positive curvature, negative curvature, and another positive curvature, and we would have a lot of inflection points. For instance, one inflection point could be here, another one here, here, and maybe here. So we have 1, 2, 3, 4 inflection points. We could label them I1, I2, I3, and I4 for the inflection points.